Hello, my name is John Harper, member of technical staff at onsemi. Today I'd like to talk to you about buck boost topologies using SYNC. The reason for discussing buck boost topology is the buck boost topology is used in energy storage systems, which is a fast-growing market. There are two basic topologies, the standard buck boost and the symmetric buck boost. Let's look at the standard buck boost. So this is the bus voltage. This bus voltage is connected to the AC to DC converter and DC to AC converter in the topology. This could also be connected to the output of the MPPT stage of a solar inverter. Here is the battery. This is where the energy is stored. So the buck boost converts the energy stored in the bus voltage here into energy in the battery. The battery is normally a lower voltage, so energy goes this way when you're charging up the battery, energy goes this way when you're discharging the battery. The topologies are normally not isolated. Why? Because this voltage is already very high. There's no specific safety requirement then to isolate the battery. In some cases you may need to do that, but then you need an isolated topology then. So this is a simple buck boost topology which we explain, and this goes up to 10 kilowatt hours. You would use this kind of system. For storage energy higher than that, people tend to use symmetric buck boost. The symmetric buck boost has easy connection to the ground of the system or the neutral point of the system. Here there's no clear connection to the neutral point. This will be the live and neutral, it could be connected to the live and neutral, for example. Here there is an intermediate level here, and that makes EMI much easier to handle. Let's have a look at the buck boost topology in more detail. Here is a symmetric circuit of the buck boost topology. And here are the waveforms for that topology. And the first slide we're showing standard CCM buck waveforms. I think this is pretty familiar for most of you. Q1 is turned on, then the current goes like this. You can see it ramping up on the blue curve here. And then when Q2 is on, so Q2 is on here, the current drops down, so Q2, the inductor current ramps down. So I think nothing new for you here. This is quite standard. We'll come to a little bit of a surprise that these exact same waveforms can cause a totally different situation. We'll come to that in a minute. So the next configuration we want to talk about is DCM. So this is the same as the other one, except we're running in discontinuous current mode and the inductor current drops to 0. What we need to watch out for here is we need to make sure that negative inductor current can't happen. So we need to turn this Q2 off as soon as that current drops to 0. In this simulation I just did this manually by making sure it happened, but in a real control you need to monitor it and make sure this doesn't happen. If this current goes negative, you'll get problems. So in both cases, we're showing here is that energy is going from the bus voltage to the battery. So it's being charged up. Now let's look at the boost configuration. I'm going to do the boost configuration. I'll start with DCM mode. So here we start off with Q2 going on. So this is like a classical boost circuit. Q2 goes on, current in the inductor goes up, and then Q1 is on. It's a kind of synchronous mode, synchronous diode. The current is then transferred to the load, just like a classical boost circuit. Again, in this case, we're in DCM mode. We must prevent negative current, inductor currents. From the point of view of the boost, obviously it's then positive current in this case. So this is the device. Q2 is turned on, then Q1 is turned on, and then when it gets to the zero current in the inductor, it's switched off to prevent the negative current from the boost point of view. Now let's look at the final version. The final version has almost the same waveforms as the first slide I showed, but the only difference is that the current is negative. So you have Q2 is on, the current ramps up, and the boost, Q2 is off, the current ramps down, and it stays in continuous mode. But if you go back to the first slide, you would see that the waveforms are identical. You have Q1, dead time, Q2, dead time. That's why it's very important to make sure you don't get the negative current. So if you have Q1, Q2 switching with a negative current, you'll get a boost situation. If you have Q1, Q2 turned on after each other without a pause, and the current is positive, you'll get the buck mode. So I think that's the most important learning which I had when I did this presentation, is to show that negative current is the thing which determines whether you're in buck or boost mode when you're in continuous conduction mode. This is the circuit for the symmetric buck boost for higher levels. And I just want to point out that the devices used for this application are typically half-bridge devices. So our half-bridge 2-pack 1200 volt SiC MOSFET module is used for symmetric buck boost applications for that kind of power level. And for lower power levels, you can use our F1 modules, which 40 milliohm or 20 milliohm devices, which I just showed. Often people like using interleaving to reduce the size of the inductors. That's the same in both the symmetric buck boost and the normal buck boost topology. With that, I hope I've given you a short insight into the buck boost topology. Thank you for listening.